So again, if you rotate 1/x about the x-axis, you get this shape, which is what's known as Gabriel's horn. So, oh, by the way, just to make our life easier, let's say that I'm just looking at the graph starting at 1. So it goes from 1 up to infinity, okay? So it's like the never-ending graph. Okay. And what I want to do is like find the volume and find the surface area. What's nice about this problem is that it also combines with some of like the previous stuff that we did before, like, finding volumes and things like that. So it's kind of like a nice mix of like improper integrals with, with like volume problems. So what is the volume? So here, like you can use like this cross-section method, a cross-section of the surface, because it's like a solid of revolution, it's just like a disk, right? Like, and so the radius of is going to be just like 1/x, because that is what you use to rotate it. So you have the radius and the volume, right? The volume, if you use the cross-section method, it would be the integral from 1 to infinity of a of x dx, where this is like the area of the cross-section, but the area of a disk, right? The area of a disk is just pi r squared. So that okay? Is that making sense so far? Some weird questions about this? Let me give you a second to copy this. Okay, so two things that I can say up to now. First, we do know this integral is finite just based on what we discussed on Monday, because this is one of these like p-test integrals. So comparing with compared to last time, like, so last time I mentioned that this converges whenever converges is, sorry, just to emphasize it, when you say that an integral converges, that just means that you got a finite number as the end result. When you say that and I'll show you this in a bit later, but when you say that an integral diverges, it could mean that it went to plus infinity or negative infinity, or just that it never like ends up having like a particular bound. Like, so divergence can mean like in plus or minus infinity, or just like no finite number that it approximates. So this integral, again, like, let me just write this a little bit better. X to the p converges for p greater than 1, and we're in the safe zone because p is 2. So this is finite, which is greater than 1, right? So we already know that this integral is finite. It is simple enough that we can just like compute it if you were curious about what the actual value is. So again, like, strictly speaking, when you do like an improper integral, the way you should think about it is like as a limit, right? So you kind of write this as the limit as b goes to infinity of 1 to b of pi dx over x squared. Okay. And then this is the limit as b goes to infinity. So what is the integral of x, 1 over x squared? That's x to the -2. So you have to add +1 to the exponent. So you get pi x to the -1. And then there's a minus that comes out of it as well. And this has to be evaluated at x equals 1 and at x equals b. So, once you get used to it, and not that I have anything against it, like if you're sufficiently comfortable with it, you can just keep it as 1 to infinity, but then you have to put like x equals infinity as a bound here, and then you just have to be careful when you do that. Like, like, again, like, it's not the end of, like, you kind of get used to it after a few examples, and then you know how that works. But at the beginning, at least, it's kind of like useful to put like this limit stuff. But like in practice, like, if you ever do like an improper integral, it's probably likely that people kind of like skip that step and then just like put one infinity like as a bounds, like so. But infinity is not like a number, so you just have to be careful, like, with some of the manipulations involving infinity. So, but in this case, it's not that bad. So you just get the limit as b goes to infinity of negative pi of 1 over b minus 1 over 1, right? Which is just going to be 1. And as b goes to infinity, right? Like the idea is that the denominator, like this gets very, 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 very big. So the fraction itself, like the entire ratio, really gets really, really, really small. So this kind of goes to 0. Like I can just put like, I'll put something like this, just saying that this goes to 0 in the limit. So you just get 1 over 1, like the minuses cancel out. So 1 times pi is pi. So like the answer for the volume here is pi. So and so what that means is that this horn or this shape has like finite volume. Or that is how you could interpret it if you wanted to, right? But like kind of like if you didn't want to talk about it in those terms, what you can say is that no matter, like here's like a more like again, because this infinity thing can be a bit shady. So one way to think about it is saying no matter how long any finite horn is, its volume is always less than pi and gets closer and closer and closer to pi, right? So if you don't want to think about it kind of like as the infinite horn, what this saying is that like, that's why the limit notation it tells you that like the volume up to length b, like it's all gets closer and closer to pi as much as you want. And then like there's nothing shady about that because it's like a finite horn. It's just that you're keep stretching it, right? So I'm just saying as you stretch it, like you're like the rate at which you're adding volume is so slow that it never surpasses pi and kind of just gets close enough to it. Is that okay? Does that make sense? Okay, so now second step is like the surface area. So what's a little bit more interesting here is like that the surface area is infinite. What is the surface area? So again, if you look at the formula for the surface area, I'll just call it A for area. It was in this case the integral from 1 to infinity 2 pi and then what, like root of 1 plus f prime of x. I'm missing something. I think I'm missing what? I'm missing f of x, right? So 2 pi f of x, right? Like this is like the formula that we used for like the previous exam, right? Uh, and then it's just like let's plug in and see what happens. So this would be the integral from 1 to infinity of 2 pi f of x. F of x in this case is 1 over x. And then the root of 1 plus, okay. So, I mean, maybe I should write it here so that it doesn't, I'll put it as an aside. So if f of x is 1 over x, which is x to the negative 1, what is f prime of x? That is negative x to the negative 2. Okay, so kind of, otherwise, if I do it inside the integral, it's a bit too messy. So it is 1 over x squared, oh, or minus 1 over x squared dx. The minus doesn't matter because everything will get squared, but still, you should put it. Let's simplify this a little bit. So this becomes 1 plus 1 over x to the 4 dx. And this is x to the 4 plus 1 over x to the 4 dx. And the best I can do here is to take in that x to the 4 out of the square root as x squared. And because there's an x outside already in the denominator, it all becomes x cubed, right? So this becomes 1 to infinity of 2 pi x cubed um, x to the 4 plus 1 dx. Is that okay so far? So good. Like questions up to this point, how manipulating things? Okay. Okay, so now I'm going to tell you how you could think about like, so I'm trying to decide, should I try to see like integrate, like, you have to be like, if you start being agnostic about this, like you don't know whether this is finite or not, like, um, so you have to determine first, okay, should this be like, do you have like an expectation on whether this should be finite or not, right? And that is why I'm going to teach you now how, because this is, I do find this like one of the harder topics of the course, because you do have to kind of develop a sense of like how the integral, like the integrand is behaving at infinity. Okay. And that, like, does take some practice. So I want to kind of give you like an insight like of how you should think about this type of like integral. So because you have kind of have to convince yourself first on whether like the integral should be finite or not before attempting to prove it. So here's like kind of like how, like an argument or as an aside, how you should think about this, how to think of this integral. So here's the thing. Again, the if here are two things that you should consider. First, integrating this directly does not seem that easy because of like this annoying one. Like that kind of ruins a lot. Like this silly one like makes your life harder, and it's like very dumb because it's just a one, right? Like and it's dumb because like the integral is going to infinity. So when as the integral goes to infinity, again, you have to think x is going to be 100, then a million, then like 1 trillion, like, and you are raising all of those numbers to the 4, right? So, and again, like that's what infinity means. Like infinity is really, really big, right? So like, or as big as you want. So in comparison to this number, this is so microscopic that for all practical, like that's how people like engineers and physicists would say FAPP, which is for all practical purposes. It is almost as if this one does not exist, right? If you just care about like how the integral is behaving at infinity, like this is so much bigger that you wouldn't even notice it, like, So what I'm saying is that when X is really, really large, right? When X is really large, like x to the 4 plus 1 is more or less indistinguishable from x to the 4, okay? Like, there's almost no difference between the two. Almost the same as, is that making sense? And if that's the case, and I'll kind of do it in a square because it's not like how I'm going to finish doing the argument, but like, well, I mean, like I'm putting all of this in, oops, I'm putting like, think like, again, this is kind of like the intuition behind it. So if you believe that, then if you just want to know whether this should be finite or not, like just think about what happens if we replace x to the 4 plus 1 here with x to the 4. So if you do that replacement, right? If you put just like x to the 4, again, they're not the same, but they cannot be that different, okay? Uh, But now this makes your life so much easier because x, like you know how to take the square root of x to the 4. That's just x squared, right? So that gives you 1 over infinity, right? 2 pi over x dx. And I don't know if you remember, it's actually part of like this p-test that I just mentioned. When you or this one, if you wanted, you could also integrate explicitly. It's just like 2 pi times natural log, right? So that, because it's going to infinity, that will diverge, right? So like this diverges either because you can do it explicitly or because you just do the p-test if you want. So this one will diverge, okay? So here p equals 1 in the p-test. Or like it's just like explicitly natural log. Um, is that okay? Is that making sense? Questions up to this point. So what I'm saying is that once you do this, what that means is that because you expect these two integrals to be more or less the same, you expect this integral to be infinite as well, to diverge, because like the one it's causing, which is more or less indistinguishable from it, diverges. Okay, so this suggests that is that making sense? Yeah. Uh, the things like in the P, sorry, based on what I was writing before, the P test just refers to when like the integral is kind of like 1/x to some power. The exponent is what we're calling P. So in this case, because oops, where are you? In this case, because we get one like just like x here is x to the 1, so that's why the p equals 1. But again, like in this particular case, you don't even need to memorize that, because like this is it's kind of like ln, and ln does go to infinity at infinity. So like that's why like the integral. So like it's not that it was necessary, but like most of these problems that you'll see are the p test will play some role, what like of some sort, like, so that's why I kind of bringing it up. Is that okay? Is that making sense? Okay, so once you have persuaded yourself that this should diverge, then it does make sense to spend resources trying to prove that it actually diverges, because if you're not sure whether it diverges or converges, like then you are going to try both approaches, and it can get stuck. You have to create some sort of like the intuition for what to expect. So the idea is to use, like, the way I would do it is to use this comparison test. So I'll kind of just replace the, if you remember, like last time about the comparison test. So I'll use the comparison test for this. So like just to remind you, the comparison test is some sort of like not squeeze theorem, but similar to that, in that it said that imagine that you have like a function g of x, and you have like minus g of x here, and then you have like a function f of x that's doing whatever it wants to do, right? And so the comparison test said that if like I'll just write it in this version, that if the integral for g of x converges, or sorry, well in this case I have to put it. Oh yeah, I'll put it. Well, it's two versions. Like in this case, since I want divergence, like the other one will but it said two things. It said if the integral for g of x converges, then the one that's kind of being squeezed converges as well. This is not the one that I want, right? Because sorry, f. And the version that I care more about is the one that says like if the one being squeezed diverges, then the other one, like the outer one, has to diverge as well. Okay. So, and the other version is that if the integral for f of x diverges. It's not making sense. So here, because that's why it's important to convince yourself first of what you're trying to do. Because since you want to show that this one diverges, you want to think about this one as being the G one. So we want to find one like an integral, which is like an integrand that's slightly below it that does diverge, like because then it would force this one to go to infinity. And more or less like it's almost in front of us because of what we had thought. I would just compare it with root of x to the 4 because like that's always slightly less. You know, this is always a tiny amount bigger than root of x to the 4. So that will be my comparison. So, even when you do this analysis, it already tells you what you should compare with. Like, and that's kind of like the nice thing here. So here's my actual comparison. Right, like so the only difference between like what I'm saying is that here think of this as being oops, I forgot the dx. So think of this one as being f of x and think of this one as being g of x. And I wrote it in a way that hopefully is clear. Like, the only change that I made in the integrand, like it to remain the same, is really I just added a one inside the square root, and that made it a slightly bigger amount. And so 70% is kind of like reasonable. But we already talked on the aside why this one had to be finite, right? Like, sorry, it had to be infinite. That's exactly what we discussed a bit earlier. Uh, so because of like the aside stuff, we already know that like or the p-test again, this is like diverges because of the previous discussions. Is that making sense, kind of? So, but again, so what is this telling us? So just to put it back together, what that means is that for this Gabriel's horn, the surface area is infinite. So the surface area. Yeah.
So like, I feel like with it having like a finite volume and an infinite surface area, so like that's not really intuitive. So is there any way to like think about it intuitively, or is it just like?
I mean, uh, like the best I think that you can do is to say, what does that mean? It means like again, you kind of truncate the horn so you don't think about the horn like Actually, have you seen the YouTube video? No, it actually does like it does have like a good discussion about that because and that's why I recommended it because you know like the problem like this is where like it does make sense to think about it in terms of units because what is like the units of surface area, for example, it would be square meters or square feet, right? What are the units for volume? They're like cubic meters, cubic feet, whatever. But in terms of units, right, it doesn't make sense for you cannot have like a statement that just says like the surface area is larger than the volume. That is ill-defined in physics and engineering because the units are different, right? So you can only make comparisons between things with the same units. So it doesn't make sense to say, like, for example, you know, like what is, okay, so just to make it more concrete, if you have like a unit circle, right? Let's say the radius is 1, right? What is the area of the unit circle? It's pi r squared, right? Which is just pi. And what is the circumference, right? Like the length is 2 pi, right? So if you're a mathematician and then we're like distribute dangerous, you just, oh, 2 pi is like greater than 5, so the circumference is larger. But no, like this does not make sense because they're things of different nature, right? This have, again, this would be meter squared, and this would be like, for example, meters, right? And it doesn't make sense to say that like, you know, something in meters squared is larger or smaller than something that is measured in meters. In the same way, which it doesn't make sense to say that 3 hours is bigger than 2 feet, you know, or like, or less than 2 feet, you know what I mean? And you know, like in monetary exchanges, you know, that's why you need a conversion rate, you know, because like if you don't know anything about your currencies, like even saying like $1 is more than €1, like that is not clear unless you have like a transformation rule between them. So the only point why I'm making this comment is because if you it right, it can look paradoxical that the volume can be finite while the surface area is infinite, but at least that kind of like dispels like the notion that one has to, you know, that they can be comparable in some like obvious sense of the word, because they kind of can they both be doing their own thing, you know, because they have different units, so like the comparison cannot be done like directly, you know what I mean? Of course, like it's still like it is paradoxical in some way, but it does become less paradoxical once you think about it in terms of the units, because then you're like, okay, but you know, you can like the statement like the area is less or more than the volume does not make sense. You know, it only makes sense to compare it to the unit. You know what I mean?
Yeah.
But I mean, yeah, but I mean, it does leave some aftertaste, like, you know, and this is why people didn't like kind of like accept these like examples for like a long time. Like they were like met with like, you know, resistance. Like, so, I mean, because they aren't supposed to, and that's kind of like, you know, calculus, like, you know, these type of examples are the ones like that did develop calculus in the sense like, oh, we do have to be careful with what we're doing because like we're finding, you know, you can easily find things that, you know, if you're not careful can be sounded almost contradictory, right? Like, you know, so but yeah, you do have to. There's like actually a cute example. It's slightly different, but it's kind of like you do get really cute shapes out of it. So I may show it quickly. Which kind of like in the same spirit, like just to, you know, like they're like these fractal curves. I don't know if you have heard about them, but they're really fun. So like the cute thing about the curve, like these fractal curves, is that they're kind of formed by a pattern where like the next curve is based out of the previous curve. So like again, I won't go into like the procedure, but like, you know, you start with this curve, which is kind of like a star-shaped curve, I guess, like, or well, it's called like a snowflake. But and then the next version of the curve, it kind of like has like a version of the snowflake attached to each of like the previous sides. And then you do step 3 and you kind of like keep iterating the pattern, right? And then let's do step like 8 or something like that, more fun. And then step 8 has like this one. And then you can do like step 24, for example. Well, and then it keeps going, right? And when I say it keeps going, I mean that you can kind of take a limit of these curves in whatever sense of the word you can. And the limit will have infinite length. The arc length of the limit curve will be infinite, but the area will be finite. Okay, so it's kind of like a 2D version of like this Gabriel Horn thing. It's they're very cute, like, you know, so a lot of like math, like art work is just made with fractals. So if you Google fractals, like there are entire books that you can buy just like with fractal artwork because they are all generated with this like self-similarity patterns, which is how they're called. So they're really cool. Well, anyways, I'm just saying that so and like again, taking a limit of curves or things like that, it is like you know, it is like a tricky business. Not that we are going to do, but I'm just saying like yeah, whenever you talk about infinity, you do have to be careful, you know. Uh, And there's okay, so before we move, there's another type of improper integral that I do have to tell you about. But before I tell you that, just to clarify something that can be a bit can be a bit confusing. So, remark. So I mentioned last time, right? I mentioned last time that if like an integral like this converges, right? And so like what I said like on Monday was like, imagine you have an integral that you know converges, and also you know that the limit of that function exists at infinity. Right. What I mentioned, if you remember, like from last class, is that this limit has to be zero, right? Like the only if the function has a limit, then and you know that the integral converges, then the limit has to be zero. Which is a more useful way to say this, which is why I brought it up, is that if this limit is not zero, then definitely this integral cannot be convergent. So it diverges. So a more useful way to say this, if limit of f of x as x goes to infinity exists, but is different from zero, then the integral diverges. Diverges. Okay. So that is what the statement I mentioned last time says. Now, so this is what I wanted to clarify because it can be confusing. This is not saying that the only way for an integral to converge is if the function has a limit. So that is not what this is saying. So just to clarify, it's still possible. It is still possible for the limit as x goes to infinity of f of x to not exist, but still the integral converges. So the only thing I said last time is that if there happens to be a limit for the function, then the limit for sure is zero. But if the function has no limit, then it's for graphs what ends up happening. And there you do have to analyze what ends up going on. Okay. So there's like a very famous example of this. Um, I'll give you like another example later on in the course once we have talked about series, but right now it's too difficult to discuss it. But there's like a very cool example about this, which are called like the Fresnel integrals. So just to illustrate this point, um, you have like these Fresnel integrals. And they're these are really important integrals, like they appear in optics and other places, like electromagnetism. So like what Euler like well, so this was shown by Euler actually. So what is it? Pi over 8. Let me see. Let me see if I have this one right. Sine. I may be missing like a factor of 2 or not. Let me see. Yeah. I think this is fine. Yeah, it's okay. So there's like there are these integrals. Like so notice like in these integrals, it's not that the sign is being squared. Like right, like sine is not squared nor cosine. It is the argument that's being squared. Okay, that's the difference. Like so it's not sine squared, it's sine of x squared. Okay, so these integrals do converge and it gives you this finite number, which is like a like hard thing to prove. Like I'm not saying like that we can prove it now, but this kind of shows you my point, because if you believe that, then like I don't know if you're like let me see if I can find GeoGebra for a second here. uh, oh, actually I can do it on Wolfram Alpha also. Well, let me do it on GeoGebra. I prefer GeoGebra. Sorry, just to go for a second, like if just to start, let's start with um sine of x, right? This is like the graph for sine of x, or like cosine is basically the same, but it's shifted, right? But it just repeats itself over and over, right? It's periodic, so it has no limit at infinity, right? Like the sine function. So this function has no limit. Sine of x squared is kind of more or less the same. It's just that the argument is being squared, so it also oscillates faster. Like you increase the period of oscillation basically. So if you do like I can do them like next to one another, so you can compare them more easily. Okay, you can totally see here like that this one wants to oscillate so much faster. Uh, like this, because the period of oscillation, if you have seen this like from angular velocity, is 2 pi over like the like omega, and like this is like going to 0. So it's kind of like all like faster and faster every single time. So it like, but it is kind of like a periodic, right? Because sine is periodic. So it also doesn't have a limit. You can totally see it has no limit. There's no way that this is approaching a particular value. And yet somehow it does have like, if you were to integrate this from 0 to infinity, what Euler proved, like, is that it goes to root of pi over 8, which is like, again, like pretty surprising. It's surprising, especially because like, the sine one does not, like this one actually does not converge. Like, that will be one of the workshop problems for tomorrow. So, but if you put like a square here, like it does converge. Basically because it oscillates so fast that like kind of like there are a bunch of cancellations that happen really quickly, and that's why it doesn't matter that much what's going on at infinity. But that's very heuristic. Like you have to sit down and prove it. But like this is a cute example in the sense that this function definitely does not have a limit at infinity. But again, if you believe that that result, like it does converge. So okay. Um, So I did want to give you that example so that like you just have to be careful with what I said yesterday, or not yesterday, on Monday. It is possible for an integral to be finite and still there not being a limit. Only thing I said is that if there happens to be a limit, then for sure that limit is 0. But if there's no limit, then like you do have to work it out. So sometimes there will be a finite number, or sometimes it won't. But there is like a more case by case basis. Okay. Um, okay. So just to we're almost done with this improper integral stuff. Like just the only other type that I wanted to mention of improper integrals is like the ones that are called type 2. So, and you'll see that they're more or less, they're related to the ones that we were discussing. So that's why I spent so much time talking about these ones. So the other type, um, is when like you have like a function that has like a vertical asymptote somewhere. So for example, it could be something like this. So here's like a vertical asymptote. So f of x has a vertical asymptote at x equals a. Okay, so this type of improper integral is not so much when you integrate up to infinity, it's more what happens if you integrate in a region on an interval that has like a as one of its lower bounds. So you're kind of trying to integrate, let me see if I can make a picture here. So you're trying to make the region of integration like, kind of like this part. So here's B, oops. I mean, it could be like on the left side or on the right side. So like one option would be how I'm showing it here on the picture, or the other option would be kind of like the same, but with like, the roles like A appearing on the right side of the interval. So something more like this. Oh, let me call this C, whatever. So like the point is that one of the endpoints is where the asymptote is happening. Okay. And this is also dangerous, right? And in fact, like, it is dangerous because like there's an infinity involved. It's just before like the infinity is kind of like in the horizontal direction because like the domain of integration is getting super large. Here, like the infinity is in the vertical direction because like the values of the function or the range, which you would call that as well, it's getting super large, right? So, for example, like for the type, so like these integrals, I mean, they kind of like both are treated the same way. But so for like the first picture, you to find like if you wanted to integrate that, you kind of do like something similar where you do kind of like a limit procedure. So okay, I'm running out of like letters here, so let's just call this like bit annoying. Like call this C. You would do oops. So it's kind of like taking a one-sided limit. Um, oh, actually, let me do the picture one more time again here. So what I'm saying is that sorry, just to go back to this idea of like truncation, what you do here is you say, okay, I don't want to do the integral directly, including a because like the function is becoming infinity. You kind of sometimes say that the function is blowing up at infinity. Sorry, at a because it's going to infinity or minus infinity. And so you kind of truncate the region of integration, and you find this instead, this area instead. Okay. And then you just ask what happens as you slowly move C towards A by taking the limit. So it's kind of like a truncated limit. Sorry, a truncated integral. But before what we were doing is kind of like moving this to infinity, and now you kind of like move this towards like the asymptote. Is that making sense? So far, so good. Got questions about that? Okay, so let me do first an example, and then I'll do kind of, there's also like a P test for them, or P series, no, P test actually. So, but let's start with something like, let's do natural log. Like, just so that you combine it with like stuff, we can combine it with stuff we have discussed before. Um, okay, so here's an example. So you know hopefully the graph for natural log of x. Right? And natural log crosses the x-axis at 1, right? Ln of 1 is 0. So you could try to do the integral from 0 to 1 of natural log of x, okay? So we're trying to determine whether this is finite or not. Try to determine. Okay. So hopefully it's clear why it would be like an improper integral of sorts, because like natural log is going to minus infinity as x approaches 0, right? So you're getting into like the problematic region for natural log. Okay. So based on this definition, because this is like a specific number, by definition, again, the idea is you kind of take like a truncation. You work on like a safe region. So my safe region goes up to the number c, and instead what I'm doing is kind of like this integral, right? So I'm not trying to go all the way up to 0 because that's problematic. So I kind of like just remove a little bit where like the asymptote happens. Um, okay, and so according to the definition, the integral from 0 to 1 of ln of x dx is a limit as c approaches 0 from the right, the one-sided limit, of the integral from c to 1 of ln of x dx. Oops, sorry about that. That okay? That making sense? So far, so good? Are we really any questions up to this point? Okay. Now, anyone remembers how we found ln before we did integration by parts, like to find the integral for natural log? I mean, so if you do integration by parts, like, that's actually the first, one of the first examples we did by integration by parts. So if you do integration by parts, I'll just remind you what it was, but I'll just give the answer. It was u equals what, ln of x, and then you would use dv to be dx, right? But if you do integration by parts, you end up finding, like the antiderivative of ln is like x ln minus x. That's what it ends up being. Okay. So, like before taking the limit, again, this is important. Before you take the limit, you just try to simplify as much as possible. You put 1 ln of 1 minus 1 minus c ln of c plus c, right? That's what you get if you do this correct. Right, so this is the value at 1, and this is the value at c. Got flipped because of this minus x, right? Okay, and then ln of 1 is 0, so you can simplify this a little bit. So this is 0, so you don't care about this one. And let me just I'll put it like c minus c ln of c minus 1, just so it looks a little bit nicer. So far, so good. Questions about this? And again, the C is like the truck where the truncation happens, so we're trying to move that towards 0. So you have to understand how this behaves as you approach 0. Okay, so -1 is fine. That's just like a constant, not a problem when you're taking limits. C is also fine, right? As C approaches 0, that just goes to 0. Now, what is about C times ln, right? That's like, if you were to put like naive limits, this would be like, I'll put it in quotes because like that's what we have to check what happens. Like you would get 0 minus 0 times ln of 0, right? Minus 1. But the point is, of course, ln of 0 does not exist. So you should really think of ln of 0 as negative infinity, right? Like that's kind of like the better way to think about this. So I don't know if this looks familiar, but this is like the L'Hopital, one of the L'Hopitals of 0 times infinity or 0 times negative infinity. This is what you would call like an indeterminate form, right? So and now how would you do this? So for L'Hopitals, you have to write the function as a ratio in order to, so this is like L'Hopital. And L'Hopital is really important for many of the things moving forward. So I'll kind of also send you like a refresher of like the basic things involved in it. But so how would you find this limit? Let's just work it out here separately. Well, does anyone remember what this, if you ever did it, does anyone remember what this limit is? 0. Well, but after you do L'Hopital, like, because if you say 0 over 0, that's undefined, right? Like, but that can be simplified further. What were you?
Write it as a ratio, like but I don't.
Yes, no, okay, so you will see why this is 0. What that means is that this is going to 0 faster than ln is going to infinity. So or negative infinity. So it's kind of like a contest of like of things, but yeah, but what you were saying is correct. You have to I'll write it as c to the -1. That's the trick, right? Because then like the numerator is ln of 0, which is negative infinity. The denominator is 1 over 0, which is also like infinity. So it becomes like an infinity over infinity type limit. So now this gives you infinity over infinity. And so now you can do L'Hopital. I'll put LH whenever I do L'Hopital. Um, so this gives you 1 over C, and the other one gives you negative 1 over C squared, right? And now you have to remember how the fractions of the fractions work, right? But like this one moves to like you do this multiplication. So these two get multiplied together, and these two get multiplied together. So you end up finding the limit as C goes to 0 of minus C squared over C, which is the limit as C goes to 0 of negative Z, which is just 0. Okay, so 0 x times ln goes to 0 as x approaches 0. So just to, I can show you that quickly. Like, if you were to do the graph of the function, sorry, just to do it for a second. If you do f of x times ln of x, that's kind of how it looks like. And see, it approaches 0. Okay. So back to the limit stuff. So back to the limit. Okay. Okay. So this, because of L'Hopital, we already know is 0. This is not a problem. This was going to be 0 to begin, like not an issue. So you just end up with negative 1. So this limit is negative 1. In other words, the integral from 0 to 1 of ln of x dx is negative 1. And so it converges, in particular, it converges because we did find its value. That makes sense. Reasonable. So this is this is actually like a sophisticated problem, because if you do everything from scratch, you have to do integration by parts to find the antiderivative for ln, unless you memorized it. Then you have to do L'Hopital's to find one of the limits. Like, it does combine a lot of like different skills. So like these problems with like improper integrals can be tricky, because like there are like a lot of things that go into like putting them together. So you kind of have to know very well how to do like each of the pieces like of the puzzle, like when you're solving it. Um, just to maybe to finish this part, let me do like this 1 over x to the p. So let's call this a p test for improper integrals, or let's call it the second p test. I'll put the bound at 1. Like, this is not such an important thing, just to make my calculations a bit easier. Like, the important thing is like that there's a 0 here, because again, like if this appears, think of p as being a positive exponent, so that one, like if you put x equals 0, then this becomes 1 over 0, right? Like if it's negative, it really is in the numerator, so it doesn't really count. But so here, p is positive. So the question is like, when is this integral finite or not? When is this integral finite? For which values of p does this give a finite result? And you do exactly the same thing where what is this integral? Uh, it is a limit as z approaches 0 from the integral from 0 to 1 of sorry, the integral from c to 1 of 1 over x to the p. How do you find this integral? I mean, it's just like you know, like the power rule. I'll write it as x to the negative p dx. And then okay, this gives you x to the negative p plus 1 over negative p plus 1 evaluated at x equals c and x equals 1. So at 1 is there's nothing too much to say, like you just plug it in and then you just get the limit as c approaches 0 of 1 over 1 minus p, right, minus c to the 1 minus p over 1 minus p. It's kind of like nicer to just write that because 1 minus p looks like more clear. Okay. So far, so good. Is that making sense? Okay, so now you just have to ask, okay, again, you're making C smaller and smaller, going to 0. So you just have to ask, how does this behave? This does not depend on C at all, so it doesn't matter for the analysis. The only thing that you really have to worry about is what's going on with C to the 1 minus P. And here, like, again, you have to think about the exponents because maybe it's good to give like some numerical examples first before like giving like the complete answer. So what is its limit? So for example, just to say if P had been 2, right? And then this is 1 minus 2, right? 1 minus 2 would be negative 1 over, well, I mean, I guess like 1 minus P, I could put 1 minus P as negative 1 in all of these. The important thing is like again, like these numbers don't really matter that much. The important thing is that you put P equals to 1 minus P is negative 1. So with P equals to secretly, it's better to think about it as this being in the denominator, right? And as C goes to 0, this being in the denominator blows up, right? It becomes like infinity. So this like wants to diverge. So this one diverges. But for example, if you had put P equals 1/2, right? If you put P equals 1/2, you would have obtained, you know, 1 over 1 minus P is 1 minus 1/2, so it's 1/2. And then C to the 1/2, which is root of C, right? But the important thing here is that because this exponent is positive, it really kind of stays in the numerator. So root of C as C goes to 0 is just 0, right? So this one would have been finite here. So what I'm trying to show you with these two examples is that what really matters for whether this limit is finite or not is really whether this exponent is positive or negative. Because if it's positive, if this ends up being positive, then this ends like it's kind of like the 1/2 case. So you end up getting something finite. So what we need here, so we need 1 minus P positive, sorry, positive, or 1 less than P. And that's a criterion for convergence. So to summarize, summarizing, this integral is finite or converges whenever P is less than 1. Yeah.
I mean, that's just like a specific case when you have those bounds, right? Or is it always vice versa?
Well, I mean, I mean, this number could have been 5, 10, 20, right? It doesn't matter because, it only affected the upper bound, it could have been any finite number, right? Like the only thing you would have changed is that you could hear like b to the minus p plus, I mean, but you just get like something finite. Now, this one is like the important one because this is where the asymptote occurs, right? So you do want, I mean, the reason why this is called like an improper integral is because one of the bounds in this case is like the asymptote. So it could not, like, you could not have chosen like, if you have chosen like 1/2, like it's not like an interesting question to ask, right? Because like everything is finite within that range. So like the only freedom that you have, like in this case, like you could have put like any upper bound. Uh, but right, like the lower bound makes sense to keep it as being 0 because that's where the asymptote occurs. Is that what you were asking, or were you thinking about?
Or like, because there could be an asymptote somewhere else.
Oh no, like for example, yeah, like but just let's just do it. Like let me give you an example quickly. Like but yeah, like say uh what do let me okay. Here's like a silly one. Where's the asymptote now? At -2, right? And that is where you would like to do the integration now. And again, like I'm just saying, I don't care about what the upper bound here is in this case. So because of this, it's just like a translation, right? Like this should converge whenever p is less than 1. It kind of works exactly the same way. And so just to wrap this up, it's kind of cute because it is the opposite, the complement to the other case. So just to finish this, like, so this is what we just found is that if you have 1 to infinity of the x over x to the p, this is convergent for p greater than 1. And if you have 0 to 1, for example, of the x over x to the p, this is convergent for p less than 1. And I mean, I don't have time to do it today, and I won't, but I'll leave that as an exercise if someone wants to try it. Do a change of variables, t equals 1 over x in the second one to reduce it to this case. Because if you do 1 of t equals 1 over x, one of the bounds becomes infinity, right? So like you can apply if you want to try it, again, for fun, like because you really don't need it, but you can try it if you want. The second case follows from the first one, using a substitution. Or u equals 1 over x, like that's what I'm trying to say. Like you do like a u sub u equals 1 over x, and if you rewrite everything in terms of u, you get like an integration that kind of looks like this, and then you apply the test for that, and you'll see what. I mean, try it if you're interested. It's kind of like cute to see what happens. So that's why I meant like they're not really that different. Like you can always do a change of variables to turn like you do a change of variables at where the asymptote is happening, and then you always turn one of these types into the first type. So let's wrap it up here, and then next week I'll tell you about sequences and mini intro to series. Although I don't think we'll do that much, but I think it's like a good place to end. And again, if you have any questions about the exam, you can make a grade request on Gradescope if you like.
It doesn't, it just brings you back to this.
Here, like the proper integrals. I'll check what is happening with the. Like I think MyLab was giving some issues yesterday. Maybe they're still persistent, but I'll check the deadlines. And if it's not working by tomorrow, you can email me and I'll try to contact the representative, like the Pearson person, like to see if like sorry.